we have our special guest, Kate Harper from AbbVie. Very much looking forward to your talk. Thorsten Rosner is here with us as well from our sponsor who's supporting this webinar, Porton. Okay, so today Kate will be telling us about a very interesting program at AbbVie where they've managed to scale up a process using visible light photoredox chemistry. I know in medicinal chemistry, these tools are very, very popular. And one of the big questions was always, how are the process chemists going to deal with this? So I think we'll have the answer to that today. Before we get started with our main program, I will let Thorsten from Porton just share a few words about our sponsor to thank them for supporting us today. So Thorsten, I'll let you take it for a couple minutes.
Thank you, Dennis. My part will be very short, and I'm just going through a couple of slides here, just introducing you to JSTAR and Porton, and essentially who we are and what we can do. So JSTAR is a contract research organization primarily supporting early phase 1 and phase 2, early phase and phase 1 projects. So on this slide here, we show a little bit our core functionalities that we have and the works that we can do across the different areas. Process chemistry, synthetic chemistry is certainly one of our core functionalities. Within this, in the synthetic part, we have the catalyst and enabling technologies, potent compound handling and kilo labs and GMP. But we also have a lot of other core capabilities, foremost mentioning our analytical development, crystallization development, drug product pre-formulation, just to name a few. And here on the slide, there are a couple of the specific services that we offer. So I'm heading the Catalyst and Enabling Technology Group here at JSTAR, and I want to give you a brief overview of what we typically do. Within the heart of it, we offer high throughput screening, specifically for catalytic reaction, air-sensitive reactions. From a process chemistry perspective, usually we try to find the best catalytic system, meaning we screen different catalysts, bases, solvents, ligands, and precursor as well to identify which system is most suitable under the different aspects and the different times of a program. However, the same technology can be also used for library synthesis, and this might be more of interest to some of the audience here then as well. So in theory, you can make 96 different compounds if you're interested in it, and isolate those ones. We have the capability to do high throughput screening for a different set of chemistries. We can do electrochemistry. For example, can screen the 48 reactions in parallel, but also photochemistry. And this is what is really transitioning to Kate's presentation later then as well. But this is more utilized on a very early part of the R&D work, try to identify if a reaction can work and what kind of wavelengths, for example, needs to be utilized under the reaction conditions. We do this very commonly for cross-coupling reactions, but also for pressurized reactions or hydrogenation reactions mostly. The reactions we can then also test in flow, like photochemistry in flow, but the photochemistry, for example, we can test them also in a CSTR. So these are continuous stirred tank reactors that are in series, and they're shown here on the right, for example. And there are the advantages, for example, that we can even handle slurries or light slurries, at least something that we couldn't do at this point. So electrochemistry is another thing that we can do in flow, which we successfully demonstrated. But most of the works that we do are on R&D scale and maybe helpful to support early discovery work as well. So I think at this point, I'm handing it over to Kai, and I'm looking forward to his presentation. I heard some of his talks in the past, and he is an exceptional speaker and presenter. So I'm looking forward to the work that he's going to share with us today. Thank you very much.
All right, thank you, Thorsten. And yeah, Cade, before we get started, I'll just give an introduction to the audience about you and ask you a couple warm-up questions. So our speaker today, Cade, was raised in semi-rural Utah, where he spent most of his childhood fishing, hiking, and enjoying the mountains. He eventually attended Brigham Young University, where he discovered his passion for chemistry and met his wonderful wife. He graduated with BS and went up the road to the University of Utah, where he worked with Matt Sigmund, developing multi-dimensional linear free energy relationships. And after getting his PhD, he performed postdoc studies with Eric Jacobson at Harvard on catalytic glycosylation. He started at AbbVie Process in 2015 and now leads the Innovative Technologies Group, exploring new tools to enable smart process development. Outside of work, Cade is a very proud father of 5 children, including 2 sets of twins, and he spends as much time as possible with them. So I don't know how you do it with 2 sets of twins and everything else you're juggling, but that's fantastic. So Cade, the audience always likes to get to know the speaker a little bit first. What inspired you to start your career in drug development?
To start the career, boy, that's interesting. So, I mean, getting into chemistry goes back to my first year at BYU, where I was trying to be a business major, skating through my classes, and then I took a chemistry class, and it was kind of kicking my butt. And so that's where I was like, I enjoyed the challenge of the chemistry much more than the accounting or the other class I was taking. So that's where I made the change. To get into the pharmaceutical industry was kind of an interesting story where I thought that I wanted to be an academic, went through that process and didn't really get anything compelling back out of it. And so it was Eric who kind of prompted me and said, hey, have you thought about industry? And I really hadn't at that point, but then I started to open my eyes to it. And yeah, the rest is history. But yeah, it was a pretty late decision. Because maybe 3 or 4 months before I took my job here at AbbVie that I actually considered moving into the industry, but I have no regrets. So,
yeah, sounds like it's going quite well. Well, since you've joined industry, what's become your favorite molecule or process?
Oh, let's see. I'll tell you probably the story that we're going to talk about today. So the product molecule, this trifluoromethylation reaction that we're going to go over, probably my favorite thing that I've encountered since I've been at AbbVie. So that ties very well together, right?
Yeah, definitely. Super cool. And yeah, so we've now got about 100 participants on this call. I know many of them are probably earlier in their careers. If you could go back in time to when you first started your career in process chemistry or starting in the industry and give yourself any advice, what would it be?
Yeah, so the advice would be this: value your time. I think coming in and the way that we kind of train chemists in academia, their time is not as valuable as it is in actuality. So make that transition as quick as you can to where you value your time as the thing of the greatest value that you're working with in lab, is the amount of time that you could spend doing it.
Oh, fantastic. Well, thank you. Well, we really value your time. I appreciate you joining us today. So with that, we'll let you take it from here.
Yeah. Thank you, Dennis and Jenny, for putting this together, and Thorsten for the kind words. I appreciate that. Let me bring up my screen here. Is that sharing the correct thing, Dennis?
It doesn't look like it's sharing yet. Oh, here we go.
Now, there we go.
There you go. Yep.
We're good. And the pointers there and everything. Good.
Yes.
Excellent. Well, so yeah, I'm going to tell you a story about Photoredox, and I think part of that ties to the existence of the group that I'm leading now, which is the Innovative Chemical Technologies Group at AbbVie, which has a really interesting and awesome license, I think, in the development space, where we're looking out at the horizon and trying to see chemical technologies that can change the chemistry that we do and also change the way that we do chemistry. So, and that's just to help try to solve this classical challenge of chicken and egg issues, especially when it comes to chemical technologies. in industry, in the pharma industry specifically, right? Which is, we think something like Photoredox, for a long time, there's a lot of cynicism about it, whether or not it could be scaled. And to try to scale that on the timeline that we have to impact projects in the process space, in the development space, really those two were in conflict with each other. There was really this need for kind of a deep dive and deep understanding. So that's part of what spawned this group, is this idea of, if we're interested in making an investment in chemical technology, let's take it out of the pipeline. Let's investigate the fundamentals and the things that need to be addressed without that time pressure that will always be kind of counterproductive towards generating the best solution. And then once we're done with that, then we can essentially kind of shelve it and then wait for the pipeline impact to come. And that's exactly how this story that I'm going to tell evolved. But yeah, that's part of the kind of the license of the group. Here is the individuals of the group. So really, I think 5 fantastically talented, wonderful people that I'm working with in developing these things with expertise across all different kinds of disciplines. So from photochemistry, electrochemistry, computational chemistry, automation, physical organic chemistry, flow chemistry. We're trying to bring all these different tools together and then use them to evaluate the process technology, specifically the future. So it's a fun space to work in, and a great group where we're, I think, hopefully pushing some of the boundaries of what we consider scalable processes. But this all has the genesis of all of this group and some of the other, and photochemistry, scalability of photochemistry for us started with myself and a colleague of mine by the name of Eric Machetta, who was a chemical engineer, who I benefited tremendously from interacting with. And it was us kind of focused on this question of how do we scale photochemistry? And we started to play around, and I put this experiment up because it really was an ill-posed experiment. It was badly designed, right? But it taught us a lot. We did this kind of experiment where we're taking these kind of cheap lasers that I'm holding in my hand here that we could buy for like $100 off of Amazon. And we were shining them into reactions. We were using LED PFRs that a lot of you know or have seen before, and then simple, CFLs, irradiating these reactions and then measuring the kinetics. Already we had the understanding, and it was well established in the field, that the way to scale this kind of photochemistry was going to be through flow chemistry. So we were measuring the rates, because the rate is an intrinsically important aspect of anything that you're going to apply flow chemistry to. So we evaluated a number of different reactions. Here I'm showing this one that Rob Knowles published, and we saw a lot of kind of common factors between these reactions. One is, obviously this is a biased experiment, and the lasers were always outperforming the other light sources that we had. But in the same time, we also saw these kind of straight line concentration independent kinetics, so zero order kinetics, which indicated to us some pretty interesting things. This was more elaborate work done by Eric to kind of lay the foundation of what we would do together. And that is, as he increased LED power in one of those PFRs, he saw a corresponding increase in rate. And similarly, as he increased photocatalyst concentration, he saw variation, not maybe diminishing returns with regards to rate. And we took this and we tried to understand this in terms of kind of the key physical processes that are taking place. And the rate law that you would determine is essentially, the rate is dependent on the excited state of the catalyst. The excited state of the catalyst is tied, of course, to the Beer's law properties of that catalyst, as well as the incident photons. So getting into Beer's law, right? One of the things that I didn't appreciate, although I've used Beer's law and continue to use it every day, but I didn't appreciate it at the time, was that if you reorder Beer's law, we think of it in its linear form, right? Absorbance, molar extinction coefficient, concentration, etc. If you rearrange that in terms of attenuation length, so how far light will penetrate a solution, it becomes a logarithmic relationship. And that's something I tried to highlight with these pictures here on the right. So as you scale linearly in concentration, you see more of an exponential relationship with how far that light is penetrating the solution. And then the other aspect of Beer's law that is still counterintuitive, I would say, is that if you introduce twice the amount of photons, you don't penetrate that solution any deeper. And that has to do with, the fundamental aspects of how Beer's law was derived. But yeah, that's something that's very interesting, right? So in this case, we're adding twice the amount of photons to the same solution. And you see it's not penetrating it any further than in the 100 milliwatt case than in the 200 milliwatt case. So those are two key principles that I'm going to come back to over and over again as being kind of the guiding light, if you'll excuse the pun there, for us in developing a solution to scaling flow chemistry or photochemistry. But it comes back to these relationships that Eric had derived early on, which is, if you're chasing more and more rate, and rate is again directly tied to the kind of throughput that we could expect. And in our world, a lot of times the time that we spend processing is the most expensive component, not necessarily the cost of the raw materials, but the cost of the time that we spend processing in facilities that are, go through government audits and things like that. That's the most expensive component. So we want to minimize that time. We want to maximize our throughput. And so in order to do that, we felt like we had a pretty good relationship to chase here in terms of increasing the power further and further. And that led us essentially away from LEDs and into lasers. Now there's high powered LEDs out there, and there's pros and cons to both of these light sources. But as the light source became more and more important in the studies that we were doing, we leaned more and more towards lasers because we could get some of the information that we wanted, as well as the increased intensity. So I highlight a few of the, some of the nuances between the two here. But one of the things that's really important with considering LEDs, right, is that they're a diffusive light source. They're essentially spraying light out from this kind of very small diode. And in order to quantify and understand how much light is going into your reaction, you need to do experiments that are known as actinometry, where essentially you take a known reaction with a known quantum yield, and you try to understand how much light is then incident based off of that. Whereas with the lasers, we could measure directly how much output light is being generated, and that correlates nicely with the kind of the current applied to the laser system. So we could have now control of the input number of photons. And all of this is helping to shape, in time, we're starting to shape these ideas as understanding photons as equivalents, as stoichiometric components of these reactions to help drive their rate even faster. The other key aspect between the two is with LEDs, of course, with any kind of light generation, you generate heat as well. So, I think all of us know that because we've all gone to change a light bulb that we just turned off and have it, maybe burn our fingers or be very, very hot. Even LED light bulbs, if you go to change them right after, they're very warm. So there's a lot of heat associated with light generation. And of course, one of the hallmarks of process chemistry is controlling the temperature of our reactions. So putting a flow reactor of any type proximal to these LEDs, we're going to have to figure out a way to sink the heat from the LEDs and control the temperature in the flow reactor, because that's a necessity for scale. Whereas with lasers, we can now take the heat associated with the light generation and couple it via a fiber optic. So just a cable, right? So I have a small orange fiber optic here, that just a demonstration where I could put the light source on one end and then have the output on another. So I can now spatially separate the two with ease. So those are two of the big highlights and things that proved to be very important about kind of our transition as we started thinking about what light source do we want to drive our flow reactors on scale. So we got very interested in this CN coupling as just an academic pursuit to understand kind of the photophysics and the other elements of the photochemistry. And we came up with some very interesting observations that helped us understand scale-up principles that gave us confidence that we could scale reactions. So in this case, as we increase catalyst concentration, counterintuitive, right? Dennis, you mentioned my background is firmly rooted in catalysis, and this is a very counterintuitive plot to anybody trained in catalysis, right? Increasing the catalyst concentration led to decrease in the initial rates that we were observing in this reaction. We would have thought completely the opposite, right? All that centered around this kind of optimal catalyst concentration, where to the left of this, we also saw decrease in rate. So the way that we explain this is we said this must be tied back to Beer's law, where as we increase the catalyst concentration, the light penetration decreases, And then it becomes more of an effective molarity argument, right? If we're irradiating less of the solution, and my counterpart Eric put this together in a nice Goldilocks slide, as we call it, where if the catalyst concentration is too dilute, we're getting light transmittance through, but we're not capturing all that photonic flux. And so that's, just intrinsically inefficient, but it's not a bad way to go about this. Now, if you have too high a catalyst concentration, then you're irradiating only a small fraction of your solution. And if you're only irradiating a small fraction of that solution, then your opportunity for other molecules to interact with the catalyst in the excited state becomes decreased relative to the amount that is actually there. So that's where you see that decrease in rate. Whereas if you adjust your catalyst concentration to the Goldilocks setting, right, the just right setting, where you would use Beer's law to understand how deep you're penetrating into the solution, then you're getting all the photons absorbed, or you can design it to absorb all of the photons. And in the same vein, you can also adjust your depth based off of that concentration. So now you can tune the reactor and the catalyst concentration back and forth. The real lesson to anybody out there in like medicinal chemistry or process chemistry is that the catalyst concentration that you want to target for a reaction has less to do with the intrinsic chemistry and more to do with its molar extinction coefficient and its photophysical properties, right? So that's where I think that idea is still very counterintuitive, right? Where if somebody came to me and asked me, now, what catalyst concentration should I start with for this photochemical reaction? I would say, well, what vial size are you using? What's the path length that you're trying to engage? Is it a 1 gram vial, a 40 mil vial? Are you trying to use a bigger reactor? And if you could understand that as a function of catalyst concentration, then you're off to a good start. So all of that led to these kind of relationships that we could develop, where we looked at light intensity, so the number of incident photons that we're putting into a solution, and then the rates. And we can now project using these kind of relationships what the rate would be, and therefore project a throughput for these reactor systems across different sizes and scales potentially. So this was kind of the first piece that gave us some confidence that we could execute a scale up, especially in flow chemistry, and potentially change reactors as long as we knew what the incident photon flux is going to be provided by the light source, which in our case was an increasingly powerful laser. So in this study, we're using now like a 25-watt laser. As long as we could understand that, then we could design the reactor below it to match that. So scaling the light source with the reactor. And we were able to do that in an exploratory way. So we scaled this to just under 2 kilos in about 32 hours. So just over 1 kilo per day throughput, which we view as kind of that enabling phase, that phase 1 type delivery that we could enable with this kind of throughput. And again, in this picture that I'm showing here, we're just using a simple single CSTR, which is just in this case an open to air reaction flask in our EasyMax. As a setup, we have an inlet, we have an outlet, we're using flow chemistry, fluid dynamics. I have the time to go into the nuances of CSTR flow, but just take my word for it that it is an equal component, or it's an equal aspect of flow chemistry as plug flow reactors, which I think many people are much more familiar with. But then we're just irradiating it using optics to shape the size of our beam. So we have a fiber optic delivering that, and then we shape the light using optics to shine exactly the amount of light and the size of the reactor coupled together. So this was a nice proof of concept, but like I said before, so I think we had solved, some of the issues that we had foreseen for scaling, and we had some confidence. So then we just sat and waited. And as we waited, we did some more thought experiments. And we did an interesting thought experiment, which is just taking some very average characteristics of a reaction. So assume we're going to use blue light. Assume a very average molecular weight, something that we all deal with, right? 350 grams per mole. How many moles of photons, how many photons do we actually need to engage that? And what's the output of the laser systems or the light sources that we would need to drive this? So if we thought about this, we need the quantum yield to get that stoichiometric correlation. I would say this is an effective quantum yield. So now we're measuring moles of product out per incident photons. we had a quantum yield of approximately 1, we're going to need 440 watts to get to this 50 kilos a day of throughput, which we would target as potentially commercial or close to commercial launch quantities. If that quantum yield goes down, we need more. That's a pretty direct relationship, easy to understand. If the quantum yield is greater, we have some radical chain character, that requirement goes up, or I mean, the wattage requirement goes down rather. So this kind of thought experiment we're going through, we're thinking getting more and more high-powered lasers, access to those to enable these kind of commercial demands that we might have, and making a more sophisticated workflow where I think Thorsten highlighted the ability to scan reactions in high throughput, identify successful reactions and successful reagents. And then we take it into another realm where we're looking at more data-rich experimentation, where we're trying to understand the Beer-Lambert law properties of the solution, the catalyst. We're looking at the effective quantum yield. How many photons do we need to drive, how many moles of photons do we need to drive this many moles of product out? And we're looking at what happens to the reaction over time. Is there darkening? Are there byproducts? Does something precipitate that might coat or interfere with the transmission of the light? And then once we do that, then we think we can maximize the rate and devise the optimal photoreactor for the system. So with that, we waited. And it was maybe like a year from the time we concluded this kind of preliminary work to when the first pipeline impact came along, this trifluoromethylation that I mentioned earlier. So we had some preliminary routes. This was a rather late stage project that was going into primary stability batches. So phase 3 enabling studies were being done. And the route that had been identified previously by my colleague Dan Mack had been kind of deprioritized in favor of a direct trifluoromethylation of this 2-chlorothiophenol, which just smells lovely. And we'd done some investigation. My colleague Tim Greamy had been investigating this chemistry, and what we found in just through the literature search is almost identical conditions have been reported by Tim Noel's lab a few years prior, where they're using CF3I, which is our desired CF3 source for this chemistry, Rubipi, in pretty direct conditions. And so I took that, I evaluated it with the laser setup that we had in lab, came back after 10 minutes, it was done, set it up again, came back after 1 minute, it was done. This reaction is done in 20 seconds, as close as we could estimate with the initial laser setup that we had. So then in about 2 weeks' time, we were able to quickly optimize the catalyst concentration, the equivalence of CF3I, not a massive extension of the conditions that Noel had reported. And we could get now, near perfect conversion in 30 seconds or less, depending on the light source that we were using. So we needed this fast optimization because the real challenge here was to take this and scale this almost immediately within a month's time to approximately 500 kilo scale. To do that, we worked with an external partner with ASIMChem. And for us, it felt a little bit like a step backwards because in a month's time, we could not get them the laser equipment and technology that we had developed in-house. That took a couple of months lead time just to get the component parts in. So we had to kind of meet them where they were at, which they had a very large LED bank. So we said, that's fine. We can work this chemistry. It's homogeneous. It's fast, and we don't need, it has a very high quantum yield number, right? So a quantum yield of almost 90. So the radical chain component of this reaction is very strong. It's almost catalytic in photons, as I think about it. But we did have a pretty large amount of energy that we had to sink out of this reaction because we had acid-base chemistry from the base and the thiol, as well as the trifluoromethylation reaction. So if we tease those apart, right, we got to sink about 30, 40 degrees out of this reaction. And we need to put it proximate to a high-powered LED bank to get this to go. So we knew there were going to be some engineering challenges. So while we met them where they were at and developed this in plug flow initially, we also encouraged them, and they did invest in some laser technology so that we could build a second generation system rapidly afterwards. We did some mechanistic analysis to facilitate the flow and better understand some of the things we were seeing in lab and make sure that we had this reaction under control. So the way that we suspect that this works is, we do the deprotonation to the thiolate, which is then much readily oxidized to the thiol radical, which then can undergo either productive trifluoromethylation, dimerization, which we do see, which is also not a dead end for the reaction. We can regenerate, and we showed that through control experiments through this disulfide can participate in this reaction. And the chain propagation element we thought most likely is I dot, although just about everything in here is a reasonably stable radical. So this is just our best guess from, kind of standard delta GET numbers. So from that, we designed a system with AsymChem where we would introduce the thiol and the Rubipi catalyst in one solution, and then in the other solution, we would introduce the CF3I gas as well as the base. So to do that, all other kind of combinations of these two components proved to lead to less stable feed solutions. So we were kind of locked into that. We would pump them together, cool them down through heat exchangers, and then pass them through the photoreactor. And in so doing, we did a number of different kind of iterations and means to control the temperature, which proved key, as well as kind of the stoichiometry of these two components coming together proved key to get out the desired product with the conversion level and keeping the impurities that we were aware of at levels that were acceptable. So we executed this. We did 6 batches, almost 500 kilos in the initial stages, and we were able to control the temperature very tightly and be able to see a little bit better results each time we ran this as we made more incremental improvements to the process. So that was great. And we got the project through kind of the initial deliveries that had to be made, but then we had enough time now to revisit what some of the causes and the liabilities of running this in plug flow were. Of course, we recognized there were significant challenges in sinking the heat from the LED bank that was proximal. I mean, the LEDs were actively cooled, but there was still quite a bit of heat. If left unattended, this reactor could get up to 50 degrees without any kind of added control from our engineering elements to control the temperature. So we wanted them to pivot to a CSTR, again, using flow chemistry, using a laser. We can now shape that through fiber optics to match the beam width to what we want and the reactor size that we want. And in this case, because the demand for photons is low, because we have such a high quantum yield, we don't need a super powered laser. So we were able to obtain a 25-watt laser there and execute this and design a reactor that gave us effectively the throughput that we wanted. So we targeted about 50 kgs per day throughput that would be adequate for commercial design of this product that this was going into. So 100 kg batches, 2-day runtime. We enhanced the temperature control through the CFTR, as well as buffered against stoichiometric variations that might be introduced by pumping. And with that, we were able to execute again multiple batches. And I'll just give you a demonstration. This was done in lab here with the setup. It's a video. So this is our high-powered laser. It's only going to run at a portion of what it can actually do. Feeds solution, so TMG, CF3I, Rubipi, pumping at approximately 500 mils per minute. And then here's the photoreactor, a single stage CSTR, inlet, gravity fed outlet. You can see irradiation of the laser, the fluorescence of the Rubipi, and then the conversion, and then direct isolation of the product from that. And because this worked so well and was so efficient in flow, we pursued fully continuous processing to a key intermediate. So now taking the photochemistry, doing the workup in flow, so fully continuous processing, and then the next reaction we amended to flow chemistry, this oxidation to the sulfone, through again a simple kind of flow chemistry setup, workup, and then isolation and batch was how we landed. So this enabled that. So with that, a high level overview of this project. Here's some of the people that we've gotten to work with, and here are their names and the contributors to this project. It wasn't done in a vacuum. I'm appreciative to them, to Dennis, to Jenny, to Thorsten, and to anybody who's listening. Thank you.
All right. Thank you, Cade. Yeah, fantastic talk. A lot of really counterintuitive insights there. Not things that would have been clear to anybody without digging into this. So super cool. Yeah, thank you for sharing. So yeah, with this, we'll start taking any technical questions. If you have any questions, please use the Q&A function at the bottom and we'll find them. I guess we have one question from Mateus Verlos, who says, reproducibility is always a problem when it comes to modern methods and chemistry in particular. Maybe, do you know whether there are any commercially available photoreactors equipped with a laser as a light source?
Commercially available, no. I think that most of the commercially available reactors still rely on LED technology. But you could characterize, and I know that greater effort is being made to characterize these photoreactors in terms of their photon flux properties. So that information, as you know, ourselves and others have emphasized that that is a key component for scale up, has become more readily available from manufacturers of equipment.
Cool. I have a question on, the scope of this. Do you feel like from doing this that, scaling up photoredox chemistry in general is sort of a solvable problem now? I know a very popular reaction, for example, in medicinal chemistry is using the carboxylic acids as a radical source. Do you think those are amenable as well, or is that going to take more work?
No, I do. I think, in fact, this is, the first of a handful that we've had. We've got a project that's active currently that, has a quantum yield of much less than one we're obtaining now, a 2000 watt output laser to help drive that. But again, yeah, I think that the understanding the properties of the photocatalyst, understanding the mechanism is going to lead us to be able to control it on scale up. So that, I think, is just again, puts the impetus back on the process chemist to dig into these reactions. But I think that the path forward for scale up we view as open. And again, like a lot of those work best with inorganic bases. Some of them work with an organic bases. We've seen them come up on the radar, been able to make limited deliveries. We haven't had one hit with a kind of a late stage compound. But yeah, I think we feel very confident in our ability to bring high value transformations that are enabled by photoredox to fruition.
Very cool. So what do you think currently the max sort of, quantity that you can deliver with a process like this is? Or do you feel like, basically it's a solvable problem to, even ton scale?
I think, yeah, you could take it out to, so the blue light lasers that are available, beyond 2000 watt systems are available at prices that are comparable to, standard processing equipment. This is all being driven by lustrous metal welding. So they need super high powers. And then we take these really cool lasers that they're building to weld metals together. And then we just make them into giant blue light bulbs. Right. And we use some of the other property characteristics of the laser light source, but it's not intrinsically as cool, because if you focus these beams down, yes, they're dangerous. But if you broaden them out to bigger reactors, but we've envisioned 3-4 stage CSCRs that are capable of throughputs that would meet any commercial demand that we've seen in the last 5 to 10 years.
Yeah, makes sense. We have another question from Suzanne in the audience. Can you rule out nickel dimerization as contributing to lower yields at higher catalyst loadings?
Let me think through that. So repeat that again, Dennis. Nickel dimerization, lower yields
at higher catalyst loading.
So with that CN coupling, what we never saw kinetics that were not photon limited, which led us to believe that the nickel cycle was extremely rapid. Whether or not its resting state or where its resting state was, I won't speak to it. I don't know if we were focused in on driving the rate, and we were never able to break that direct correlation between enhanced power and enhanced productivity from the reaction. So in other cases, we have seen that relationship start to break down, but that has nothing to do with nickel. They were in other systems. So where the intrinsic kind of chemical kinetics start to become the limiting step.
Gotcha. Interesting. So we have another question from, Suzanne was asking if you see it as a deactivation pathway for the catalyst.
The nickel dimerization?
Mm-hmm.
Possibly. Like I said, in those cases, we did not probe the nickel catalytic cycle just because it never appeared on the kinetic radar that we were interrogating the reaction with. So Yeah, but I suppose that, I mean, we're using relatively high nickel loadings as well. So,
We have a question from Maria Gonzalez, who asks, in this case, you are able to use a very small amount of catalyst, but in this or other cases, how do you remove the catalyst in the workup in flow, or how do you isolate your compound at that scale?
yeah, so I'll speak to the first point that she's making there, because it was very interesting, right? Rubipi has an extinction coefficient, and in fact, I think I like to emphasize this point with people because it is, again, kind of counterintuitive, but this was a reaction that we ran a long time ago where we knew that we had three competent photocatalysts for this transformation, a pretty basic transformation, well known. And what we saw is if we adjusted the concentration of the catalyst based off of its Beer's law properties, what we saw was essentially within experimental air identical rates. So that kind of told us, I mean, photoredox properties matter for enabling chemistry. But once you have chemistry that works, as long as your photocatalyst can hit the redox properties that are required, then it's the Beer's law properties that take over that will drive the catalyst loading that you need. So we did 0.01 mole% to penetrate 5 centimeters. That's about how that broke down. There was some reaction darkening that we had to compensate for, but that's essentially the design. But of course, Rubipi has a relatively high extinction coefficient, almost 15,000 under the so something like an iridium PPY, that's 1/5 of that. So we would have to use five times more effective catalyst to get that same 5 centimeters of penetration depth. But like mesacrodinium would have been slightly better than that, and 0.05 mole% mesacrodinium versus iridium. None of these are probably going to affect the cost of goods going into this. I think we were able to obtain Rubipi at like effectively maybe $5 a gram.
Wow.
And so the amount needed to process the 100-kilo batch was less than $1,000.
Wow.
So that doesn't show up on the radar when it's that little at that largest scale. So yeah, using a catalyst with good kind of extinction coefficient, something that's going to harvest the light very efficiently, is going to be key. So what was the second part of the question? Because I get off on a little bit of a soapbox when it comes to that.
Whereas I think it was asking about how do you remove the catalyst?
So in that case, simple water wash. But I mean, obviously that's going to be highly variable depending on the catalyst and the reaction that you're trying to run. So when we did the fully continuous processing, we actually do 2 water washes, and that's just to more effectively remove the TMG salt. I believe that the photocatalyst is mostly gone. Of course, in this case, we're reintroducing ruthenium trichloride in the next step for the oxidation. So we didn't necessarily measure to what level we got the ppm, but visually, the solution becomes much clearer, and you eliminate some of the red color that's indicative of Rubipi.
Makes sense. So the next question is probably related to your Beer's law as well. So they're asking, part of the amenability of this project seems to be the crazy fast rate of reaction. Have you looked at photochemical reactions with longer reaction times on the multi-hour time frame? What are the implications at these larger scales for running relatively high power photoreactors for such extended times?
So that's a great point. Those are kind of the weeds that we're myself and more over some other colleagues are working through right now. That's one of the niceties of a CSTR, is that you can enable a higher, you have kind of this control, this balance of resonance time and volume, right? Whereas if you're going to a PFR, you're going to get to, don't have as much control over the volume and the irradiated area of a photoreactor that you might design. So yes, we have broached hour-long resonance times. Anything much past an hour is just a general challenge for flow chemistry in any reactor type. But yeah, we've kind of broached that and thought about, okay, what sinking all this energy back out of the reactor. So if we apply, say, 2000 watts to the front end of the reactor, we need, if there's a lot of thermal decay, to be able to chill the reactor to that extent. That's not as challenging. I've shown all glass reactors up here, but you can easily change this to stainless steel. That gets around a lot of the EHS challenges of using so much radiation. So you basically encase the light, nothing's escaping a steel, and you get better heat transfer properties. So yeah, we've broached some of those. I don't view that as necessarily a deal breaker. There is always that kind of challenge of at a certain level, flow doesn't become as practical. But that's not unique to photochemistry.
Yeah, makes total sense. Okay, cool. Well, thank you for this fascinating talk. Really appreciate it. Very exciting stuff. Sounds like, you know, there might be another Nobel Prize in the future for photoredox chemistry, as we've talked about. Might be to one of your consultants there. I saw listed on your slide. So very cool. All right. Well, thank you, Cade. Really appreciate you being with us. And with that, we'll wrap up this webinar.
Thank you, Dennis.
All right. So